Hello everyone, my name is Javier Velázquez, and in this TeraFlowSDN Hackfest I will be presenting one of the new components, which is the Network Slice Controller. So this is the agenda for the presentation. I will first give a presentation of the participants of the development of this new component. Then I will provide some background and motivation that made this development possible. Then I will comment on the architecture and the general description of the Network Slice Controller. Then I will provide the current status of it, and I will finalize with a demo and tutorial explaining how you can test this component and use it. Okay, so first of all, I will be presenting myself. I'm Javier Velázquez. I'm part of Telefonica digital innovation. Me, as well as Luis Contreras, we work on the IP development group in the innovation area of Telefonica, and we are now part of a new module development group, MDG, in TeraFlowSDN, and we will be contributing with this component, the Network Slice Controller. So you have here our names and emails in case you want to contact us as well if you have some doubts. Luis Contreras is the leader of this group, and myself, I am the main developer of the component. So to provide some background and motivation, the first thing I would like to address is this question, which may seem very simple, but I think it is important to address and to comment that it's important to define what is network slicing, because it is a very broader term, and sometimes it's important to define it first in order to then explain what is the motivation for the development of this component. So we start from the basis and we start with network slicing. So I provided here several images here, which basically represent various situations where there are a huge concentration of people in the same place, in a stadium, in a concert, in a street, whatever. But in these cases, in these situations, the problem that people may encounter here is that their connection to the mobile network it's very pure and with poor performance. This is because the mobile cell site it's oversaturated with many people trying to access it, and the result is that the performance and the experience becomes really bad. So network slicing tries to solve these issues, this experience, by providing a customized connectivity service with some specific capabilities and characteristics, which means that it is able to reserve some characteristics of the network, some resources in the network for users to improve their experience in these particular use cases. In that way, they can access the internet and have a normal or even a premium experience, even in situations like this with the a network that is saturated. So to understand this, this term network slicing and these definitions were firstly addressed by 3GPP when defining 5G. They defined it as I mentioned, as a customized connectivity service with specific capabilities and characteristics, And in this image you see on the right, in the upper part, they mentioned that these network slices involve a set of network functions and resources involving the core network, the access network, and the transport network. But they do not fully address how these functions are really connected. In this way, the transport network is somehow delegated to other systems. So in this way, 3GPP defines network slicing for core network functions and run network functions, but it does not specify how we connect these functions and how we provide connectivity and slicing in the transport network. So just to mention that this network slicing is more developed in the network resource management model, which is defined in the technical specification 28541. And I mentioned about this gap in the transport network. This is covered in the by IETF that I will show in the next slide. So IETF is another standard development organization that is covering this gap and is providing network slicing in the transport network. So they define this term, which is IETF network slicing, that first of all, it was defined in the RFC 9543, a framework for network slices in network built from IETF technologies, where they define an IETF network slice as a logical partition of a network that enables connectivity between a set of STPs with specific SLOs and SLAs over a common underlay network. Related to this, the SDPs we mentioned here these are service demarcation points, which are just the endpoints of the connectivity, which in this 5G use case would be RAN network functions or core network functions. And SLOs and SLAs are service level objectives or expectation, which are basically the characteristics of the slice, such as latency or bandwidth or security or whatever. And it's important to mention that these IETF network slices are not restricted to 5G and mobile networks. They can be expanded to other domains, such as private networks or data centers, whatever. It can be expanded, and it's not restricted only to 5G. So we can say that this use case this IETF network slicing comes from this use case of 5G slicing, but it can be extended to other domains. So the IETF basically defines these network slices as logical partitions of a network between different endpoints and with characteristics, and a service provider can deliver this kind of IETF network slice for a customers by realizing an IETF network slice in the underlay network. The following stakeholders that participate in this process are mainly three. First of all, we have in the upper part of the image in the right a network slice orchestrator, which comes from higher level operation systems. And then we have the IETF Network Slice Controller, which is the component we have developed and that we will explain further. And finally, we have network controllers that operate over the network, such as TeraFlowSDN. And let's now continue with the architecture. Here, so the network slice controller, which we will now call NSC for simplicity, it is a network controller that orchestrates the request realization and lifecycle control of IETF network slices. In one way, it consumes IETF Network Slice service requests and implements them using an underlying technology, and for that it has a northbound interface consuming this request and the southbound interface, and it basically maps abstract IETF Network Slice service requirement to concrete technologies, establishing connectivity and allocating specific resources to the slice. So in somehow the NSC is like this join between the 3GPP and IETF. So basically this component covers these two domains and joins them to provide this end-to-end network slicing from the 5G with the slices in RAN and core, and also in transport. Let's continue with the components that have these, well, the modules that have these components. So we have in first place the mapper, which is the first component that encounters the request when arriving to the NSC, which basically processes this customer request, putting them into the context of the overall slices in the network, and then we have the realizer, which processes the complete view of transport slices and decides the proper technologies for realizing it and trigger the realization. Regarding the current status, this is mainly the status of the components. So for the mapper, we have developed a translator, which basically the translator basically converts the slicing request coming from the 3GPP into the IETF Network Slice service request, or in case that the request comes from the IETF, it does well, it bypass this module. Then there is an intent processor which has an interface to interact with planner, well, with path computation engine components in case there are needs to calculate some policies and so on for traffic, and this development is in process. And also this IETF intent processor performs the network resource partitions and maps slices to these network resource partitions. In the case of the realizer, there are several modules here. First of all, there is a module called realization selector, which is has the task of selecting and deciding which technology is going to be used for realizing the slice. And then we have the different realization technologies. In the case right now, there are two main different controllers supported. I will go first with the IETSI NE2, which is basically a network emulator that emulates a channel with different characteristics and basically allows simulating slices in the data plane. So we have support for this component, configuring delay, throughput, and packet loss. And then the other controller supported is TeraFlowSDN. And basically there are two technologies supported right now, layer 2 APNs and layer 3 VPNs. Well, it's important to mention that in the Hackfest we will be working with layer 2 VPNs mainly. So for the interfaces, we have the northbound interface supporting 3GPP network source model slicing request and IETF network slice service request, and in the southbound we have support, as I mentioned, to the IETSI NE and TeraFlow, and we plan to support in the future, and in this Hackfest we will work on that, IETF layer 2 and layer 3 VPN models. Regarding the API, it handles the creation, exposition, modification, and deletion of an slice at customer view. Right now, this API only acts over the network controller. Well, only the creation acts over the network controller, and in this Hackfest we will also check how to address modification and deletion. And also we have a database storing the IDs of realized slices. Also, we have a web UI in development, and we have plans to integrate it into the TeraFlowSDN web UI. Let's now go on with the step-by-step tutorial and demo. So at the end of this tutorial, you will be able to test and try by your own the NSC and do your own test and get in hands with this component. So you have been provided a virtual machine which carries all the content needed for the Hackfest, and apart from that, well, you will need a device with the following characteristics. You see 60 gigabytes of storage, 8 gigabytes of RAM, and 4 virtual CPU cores. And apart from the machine, which will be used in VirtualBox 7.0 or higher, you will need Visual Studio Code with the remote development extension. Okay, so first of all, you will need to go to your virtual machine, the .ova file, and import it into VirtualBox. Once you have this, you should first configure the NAT network with these characteristics. So if I open my virtual machine, you would need to go here to Tools and Network Manager, and in NAT networks you should have this TFS NATnet. If you don't have created, you should create it and have the following characteristics, which are the IPv4 prefix, this one 10.0.2.0/24, and enable port forwarding with these characteristics. First one is HTTP with protocol TCP. Host IP would be this one 8080, and guest IP 10.0.2.10 and guest port 80. And the same with SSH, changing the host port as 2200 and the guest port as 22. Okay, so apart from this, well, you have some screenshots here in case you need to check, and you have to attach this NAT network to the VM. So I have here TFS VM. If I go to settings, I will open it here. I will go to network, and you should have in adapter 1 check this, enable a network adapter, and have it attached to NAT network with the name TFS NATnet. Okay, so once this is done, next step is booting the VM from VirtualBox, and you should install the remote development extension of Visual Studio Code. If we go to Visual Studio Code, once the remote extension is installed, you should have something like this, the Remote Explorer here for your remote machines. And if you click here in the left down part, you click to connect to host, and then configure SSH host, and you click this first one. You should include this to access the TFS VM machine, which is basically putting the host as TFS VM, the host name localhost, the port 2200 and the user TFS. Okay, and once this is done, you should connect to TFS VM and with the password TFS123. So once we are connected to the virtual machine, we should first deploy TeraFlowSDN in the machine. So we should run this this command kubectl get pods TFS and check that the pods are running, and if they are running we can open the TFS web UI at this link and load the topology by importing the network topology Hackfest JSON you have in the materials for this Hackfest. So in the machine we can get this command and you will see here that everything is running, so we can access the TeraFlowSDN machine. I have already loaded the topology, but if you want to do it, you should click here and upload the file I mentioned before. Okay, so now the next step is deploying the NSC. So in principle in the machine the NSC repo is ready, but in case it is not ready, you should git pull and change to the Hackfest branch Hackfest 7, and if you have and then you have to activate the virtual environment by doing source bin activate, and finally running the NSC with python 3 app.py, and then we will be able to access it in localhost 8080/NSC. So I'm going to do that in the machine in case you can see. So I'm gonna enter the NSC Hackfest 7 folder, and directly I'm already in the Hackfest 7 branch, and right now I'm going to activate the virtual environment to start the application of the NSC. So now it is ready, and here I have access to the Network Slice Controller API. Okay, so now what we are going to do is now to test submitting a request, a slice request to the NSC. So here we have the API, and we are going to go to the post API, select a file, and you are going to select the slice request file JSON that you have been proportionated in the files of the Hackfest. So if you execute, after a while we have a success. We see the characteristics of this slice. You see here that we have 2 megabits of bandwidth and 5 milliseconds of latency, and if we enter the TeraFlowSDN controller, here if we access the service, we have this service created which is a layer 2 VPN between these devices, and with the characteristics we mentioned, 2 megabits of bandwidth and 5 milliseconds of latency. We can also play a little bit more. Here you have a get. You see here the whole slice with the IETF template and the slice ID, and you can also delete it here. If you click it, you have success. So transport network slices deleted successfully, and if you check here, we have now a not found, which means that there are no slices as we have deleted it right now. So this was all from my side. I hope it was helpful for you, this Hackfest and all this explanation. And in case you have any doubt, you can contact me, and hope you can test and try the NSC and have success in your developments with it. So this is all. Thank you very much for your time, and see you. Bye.